Now moving into is chapter 12. We're going to do a little bit of bouncing. Still haven't quite decided how I was going to do chapter 12 and 6. I think I've left this formatted right now to do 12 a little bit, then do 6, then do 12, then do 6. I think I changed my mind on that too, but I don't think I fixed the slides. I'm going to post, so record and post a lecture about chapter 6 in bulk. Okay? All chapter 6 is nomenclature, which really just comes down to practice and knowing the rules. So there's very little for me to lecture on except here's the rule, here's an example. Here's the rule, here's an example. It's really boring. Okay, so what I'm going to do is post some information on that, and then on Tuesday we'll go through and work some practice. We'll pass out kind of an activity. You guys can work together on it, get that figured out, and start processing the nomenclature or the naming process of molecules. All of this homework is posted to Canvas, and I think a little bit more because we actually have to finish with chapter 12. The one section of information for chapter 12 that's not on here might not get covered on the exam just because of time issues. Okay, it involves three-dimensional shapes, so if you like three-dimensional shapes, good for you. You'll like that section a lot. Okay, and I don't mean that kind of mean. I actually like three-dimensional shapes too. Okay, so let's go ahead and get started with this. What happens with chemical bonding? What makes the bond? So if we take two nitrogen atoms and we bring them near each other, eventually they can form a bond. What's making that bond? Okay, the first thing that's going to interact between those two atoms are going to be the electron clouds. Of the electron clouds, which part of the electron cloud is going to be the most important to look at? The one closest to the nucleus or the one furthest from the nucleus? Furthest from the nucleus, because that's going to be the first thing to impact. Okay? And eventually what we would hope happens is we bring these in with the perfect alignment, perfect energies, all that fun stuff in a lonely electron on one nitrogen. See, that's a bad color. Maybe blue? Blue looks a little bit better. One electron on that nitrogen is feeling a little bit left out by its nitrogen, so it says, I want to find another nucleus, okay, or some other place to orbit around. If we bring those two atoms in the perfect alignment and energy near each other, that electron says, hey, I like that atom, and it jumps over there. If at the same time we have another electron on the other one that says, hey, I like that atom, and jumps back and forth, what we've got now is a sharing of electrons between the two atoms. Once we've now shared these two electrons, we've now formed a bond. Okay? The electrons jumping back and forth existing on both atoms forces those atoms to stay near each other. Okay? And that's where our chemical bond is forming. So it's all about the electron clouds, and the name that we would give to the electron cloud that's the most important part, the valence electrons. Okay? So we can look at our electron configurations to try and predict what's going on with chemical bonding. Okay? Would we predict all bonds to be the same? So in the first case, we had two nitrogen atoms come near each other. We don't necessarily need to know they're nitrogen, but they're probably the same type of atom. Why would we say they're the same type? Same size, same color. All our physical observables would suggest they're the same. If we move to the next example, guess who made which one? Move to the next example. Okay, would we predict the bond formed here to have the exact same properties as the bond formed up top? No, why not? The atoms are different. How do you know the atoms are different? Different colors. Okay? So what we have to start to evaluate is, hey, we've got something different when different atoms interact with each other. Problem that most students encounter is as soon as we find something that's different, what do we have to do? Is there, sorry, go ahead. Kind of not really. So we could gain and lose electrons. It's even easier than that. Okay? Am I different from everybody in here? How do you know I'm different? Shoes works. So we're looking at physical properties. Do you walk in and say, hey, that dude's different? Or that's shoe dude. That's hat dude. That's red hair dude. Sorry, I'm being sexist here. That's blonde haired dude. Dudette. Sorry, my bad. That's blonde girl. Woman? What's the opposite of dude? I don't know. Okay. Chick. Blonde chick. That doesn't sound any better. Okay. We don't call each other based on our physical observations. Typically, what do? We use names. So as soon as we find that there is something different, we now have to come up with names. So we would refer to our bonds according to some characteristic of that bond. Okay, so we have to give it a name. Further, we would then group similar bonds according to their particular characteristics, according to maybe their chemistry, okay, or the types of bonds that they've got. Okay? So that's a lot of what Chapter 12 is about, is looking at classifying the different bonds and what we can do with those once we've got them. Okay? So our types of bonds, I'm not a big fan of this flowchart, but it's what your textbook gave you, so we'll kind of work with it. We get two main types of bonds, ionic bonds and covalent bonds. An ionic bond is defined typically as a metal and a nonmetal. So at its easiest representation, if we take a metal and put it next to a nonmetal and they share electrons, we now have an ionic bond. Okay, well, what happens if we take two nonmetals and bring them near each other? Well, now it's not ionic because we don't fit that definition. So when we're looking at covalent bonds, we're looking at two nonmetals. Are these the only two possibilities that we have? You should be able to think of at least one more. Metal and metal. That's not on our definition here. Thankfully, we don't have to worry about it. And by thankfully, I mean I know nothing about them. Okay? We're looking at metallic bonds when we put a metal next to a metal. Okay? That's going to change some of those properties. There's another category in here that becomes more important in organic chemistry and that we will talk about towards the end of this chapter. Okay? In a covalent bond, one of the extra definitions is that we are sharing electrons equally. So when we bring up a hydrogen, whoops, come on, pen, a hydrogen near another hydrogen atom, they would share their electrons completely and equally. How would we know they share their electrons equally? What was that?
They have the same electron. They both have one.
The same electronegativity. Okay? We're looking at electrons in the bond between those two. Okay? So it's the process of how those electrons are shared back and forth. In a covalent bond, we're saying that the electrons are shared equally. The only way we can get electrons to be shared equally is if the atoms on the opposite ends of that bond have the exact same pull on the bonding electrons. Okay? So we're getting equal sharing of electrons. What happens when we move up to an ionic bond? And we say pick sodium and chlorine. What happens to the electrons in that bond? So now do you remember your trends in electronegativity? What did we say was the most electronegative? Fluorine, upper right-hand corner, lowest electronegative. Cesium, our lower left. Where's sodium relative to chlorine? Far left, sodium is closer in chemical properties to cesium than it is to fluorine. What does that mean? Sodium has a very low electronegativity. Chlorine has a very high. Where do the electrons in that bond spend most of their time? They tend to jump and go to our chlorine. So in an ionic bond, we get a very uneven sharing of electrons. It is so uneven that we say there's no sharing. Okay, we're looking at sodium completely getting rid of its electron, its valence electron, and chlorine completely taking it away. Okay, just kind of an odd concept. Because when we look at a bond, typically when we think about a bond, it's how they share electrons. Okay, so ionic is the complete opposite as far as bond characteristics that we could look at. Okay, it's a complete uneven sharing of electrons. is there any gray area between that? What happens if I took, say, an oxygen and a hydrogen? What bond do those classify under? If they were ionic, we would have a metal and a nonmetal. Okay, I know hydrogen's in a weird spot. Hydrogen kind of dances on your periodic table. We classify it according to its chemistry under group 1, because it has that one electron. But according to its bulk properties, chemical properties, it actually shifts over to our nonmetals. Okay, so sometimes you can see hydrogen written in two spaces. One space where it's located right here, and another common space is right above fluoride in your halogens. Okay, so what is hydrogen as far as a compound? Metal or nonmetal? Nonmetal. What is oxygen? Nonmetal. Nonmetal and nonmetal means covalent. But what did we say about covalent? Sharing of electrons. Complete and equal sharing of electrons. What's our difference in electronegativity? This one gets a bit weird. This is one of the reasons why hydrogen is difficult to process. I really shouldn't have picked hydrogen. Let's do something else. Let's pick carbon. Okay. Still nonmetal, nonmetal. Do we expect a large difference in electronegativity? A little bit difficult because you guys haven't looked at your tables a lot. There's a pretty big difference in electronegativity between oxygen and carbon. If there's a big difference, are those electrons going to stay evenly in between the oxygen and the carbon? No, they're going to preference one atom over the other. Turns out in this case, they spend most of their time with our oxygen. So that's interesting. We're starting to build a pseudo-characteristic like an ionic bond, but we still have sharing of electrons. So it doesn't really fit as an ionic bond. It doesn't really fit as a covalent bond. Okay, so there's a third category that kind of fills the gap between ionic and covalent. It's known as your polar covalent bonds. Okay, so there's your first introduction to those. We'll look at those a lot later. Okay, probably next week if I didn't change the slides around. So when we go through and look at our two options, we've got ionic bonds and covalent bonds as our big categorizations. Okay? When we're looking at ionic bonds, we typically represent them based on a formula unit. We'll talk about that in a second. In covalent bonds, we look at them as molecules. Okay? And the big issue or the big difference there is molecules are independent of the rest of the structure. Okay? They can be all on their own without a problem. Whereas if we do ionic bonds, with those charges there, we want to stabilize those charges as much as possible. And so we end up getting our large extended lattice structures where we put a sodium there and our chlorine there. And we could then repeat this pattern indefinitely. So a formula unit is a little bit more difficult to process because we're looking at the smallest possible combination within the overall structure. Okay? Whereas a molecule is its own special entity. We don't have to look at how it's related to other things. And we've got a picture here in just a little bit. Okay? Oh, there we go. Just talked about that with hydrogen. So let's take a look at ionic bonds first. Okay? When we looked at our ionic bonds, our classic example for a metal and a nonmetal be sodium chloride. If we look at the difference in electronegativity between sodium and chlorine, it's huge. So what ends up happening? Sodium picks up a positive charge, loses its electrons to the chlorine, and chloride gets that negative charge. Okay? So we end up now with a separate categorization. Instead of looking at these as atoms making a molecule, we're now going to look at them as ions making a molecule. Our positive charge is always known as the cation, and our negative charge is always known as the anion. Okay? So which atom should show up as our positive charge? Sodium, blue. So we could say Na for our sodium. If we're going to look at an ionic bond, what do we say the definition of our ionic bond was? Metal and nonmetal. Which one's going to be our positive charge, the metal or the nonmetal? Metal. Far left of the periodic table, we're looking at what charges? Positive. It's easier to become that noble gas by giving up those electrons. So our positive charge atom is almost always a metal. Okay, for this class, it's almost exclusively a metal. What happens when we move to our negative charge? Which atom is going to be our negative charge? We'd have our chlorine. Should include the charges on these. And if we were going to look at our definition of our ionic bond, what type of atom is going to pick up our negative charge? Our nonmetal. Okay? Because we have this pattern of these positives and negatives, and we've already established that positive and negative is bad, we want to neutralize those as much as possible. And that's what this picture is trying to show. Everywhere that we've got a positive charge in our purple, we'll have a green charge near it. Why? Okay, we could look at sharing. Why would they share? Is a positive charge particularly stable? No, it's charged. How do we stabilize positive charge? We need to bring it near something negative. What atoms are going to line around that positive charge? All of our negative ones, or our anions. The other way we could look at it is let's ignore stability by putting the negative charge around it. Let's try and put another sodium atom or sodium ion near that positive charge. What happens? They repel away. Okay? So when we look at ionic bonds or ionic structures, they tend to have these very regular complexes where we get super organized, get these alternating charges all the way through it. This tends to give a very regular crystalline solid. Okay? It's almost always going to be solid because we're trying to neutralize those charges. We're trying to put a strong attractive force between those. Okay? So you typically see these as solids. And they also end up being crystalline because of that regular organization. Okay? So the next thing we can now introduce is ionic radii, because now we have ions, we don't have just elements. Is that going to affect the size of our atom? Okay, well, what do you think? Should it affect the size of the atom? What's happening when we make an ion? We're gaining electrons or we are losing electrons. What determines our size? Nucleus is a marble inside the superdome. It's ultimately our electrons. If we start changing the amount of electrons, what's going to happen to our size? It should also change accordingly. Okay, so if we take a look at our sodium atom and our chlorine atom, and we look at their sizes, sodium starts out much larger than our chlorine. We're effectively we are in the same row. Okay? In this case, we do apparently see a big size difference as we look within that row. Okay? Why does it get smaller as we go left to right? Okay? Our nucleus is having an effect because our electrons are going into the same energy level. That's why they're in the same row. Since our electrons go into that same energy level, they're now at the same distance. So we put in more positive charge, the electrons have to get drawn in tighter. Okay? So our radius shrinks down. What would we predict to happen if we now make this a metal? What are we looking at? An ionic bond. If we now form that bond between them, what is sodium going to do in the process of forming that bond? It's going to give up an electron. So it should go to sodium ion. What would we expect to happen to its size if it gives up that electron? It should get smaller because it's lost that electron. Okay? How much smaller should it get? Well, what's its electron configuration? We look at our electron configuration for sodium. Oh, do I really want to draw that all out? I can't do that. We've got neon and sodium, which would be 3s1, right? We remove that 3 electron. That electron's the furthest one away, right? If we remove that, we start to look like what? Neon. What happens is we move up and down our periodic table. Okay? If we move up, what happens to our radius? It gets smaller. What happened when we removed that electron? We move from being in the third row to second row. We would expect a fairly sizable decrease. What happens as you go left to right? Also decreases. So we went from the extreme left, sodium, to the extreme right and up. What's going to happen to the size? It should really shrink down, okay? Because we've decreased in energy and we're putting all our electrons really close. So the size of our sodium atom should actually be a little bit smaller than the size of a neon atom. Why smaller? How many protons does sodium have versus neon? Sodium has one more proton. They have the same number of electrons, but sodium has more protons, can hold those electrons even tighter in. So we would expect something a little bit smaller than the size of neon. What happens with our chlorine? If we look at chlorine, we've got, again, our neon configuration, but now 3s2, 3p5. If we add an electron to it, that's going to become 3p6. We've added an electron to make it look like argon. Okay. Chlorine has its particular size, or that smaller size, because it can pull those electrons in. If we add an extra electron, can the protons in the nucleus hold that very tightly? Not very well. So what happens to the size? It should balloon. Okay. Let me do that picture there, and then, yes, what's your question?
You raised about to say when you were writing out the coordination, shouldn't you have to put a charge on that when you made it 6 instead of 5?
Good call. If I had specified it, yeah, I definitely should have broken that up into 2 steps. So if we wrote it out as chlorine, neon, what was it, 3s2, 3p5. If we were going to move up to the ion, I really should have said chloride is neon 3s2, 3p6. Your charge would get noted at the front. Okay. So when we go through and do our ionic bonds, we see a couple interesting concepts. We've got that metal and nonmetal. We're now also looking at ions. And when we all of a sudden shift to being ions, our atomic trends, okay, the periodic trends in our radii also change as well. Okay. The more electrons we put in, the bigger we get. So we end up seeing the reverse across our periodic table. Okay, so when we go left to right, for our ions, the ions actually get bigger from left to right. Okay, whereas before we saw it decrease. Okay, sorry, were there questions on that? Okay. Sorry, I didn't shift the slides around the way I thought I would. So this is going to be a little bit of a repeat. You'll see more of this lecture this weekend. So I'm going to record this, and I do fully expect that you will watch it and come in prepared on Monday to actually work some nomenclature problems. There is a sizable amount of slides when it comes to nomenclature, so be aware of that. We're going to start kind of an introduction on that instead of doing the rest of Chapter 12. So we're now going back to Chapter 6, or going into Chapter 6, to look at naming. So now that we've got an understanding of what ionic bonds are, we want to be able to name these compounds once we've got them. Okay? Good or bad, depending on your preference, chemistry is actually really awesome as far as naming goes. You get the International Union of Pure and Applied Chemistry, or IUPAC, came along, so a big group of people got together and said, these are the rules on how you name compounds. These are the only ways to name these compounds. If you change the format from this, you are wrong. Okay? And so there's pluses and minuses with that. Number one, if you change the name around a little bit, you could probably still figure out what compound you're talking about. Okay? However, it could become confusing if instead of having one name, say for sodium chloride, we now have 3 names. We'd have to figure out which name, what exactly you're referring to. It takes time to process and go through that. Okay, so IUPAC is good because we've got these rules. The bad part about it, you need to know these rules. Okay? They can seem arbitrary at times, When you move into, if you move into organic chemistry, it gets a whole lot worse as far as nomenclature goes, because it really is strict, just these are the rules. Here in Gen Chem, it's not quite as bad in my opinion. Okay? They do kind of make sense. For those of you that like biology, have anybody taken a biology class? What's the consistent nomenclature system in biology? Yeah, silence is a pretty good one on that one. Biologists have not come up with a consistent nomenclature system. Okay? And a lot of it comes from how things were discovered. You didn't get enough angry people together to say, this is crap, we're going to come up with a standard naming system. So if you move into biochemistry, when you asked about enzymes and different reactions, whoever discovers it gets to put a name on it. Sometimes that name makes sense, sometimes it doesn't. Okay? But you don't get a consistent ruling system. Okay? So with our ionic bonds, there's two classes of ionic bonds that we can look at. We've already looked at the simplest of them, and that's our binary ionic. Okay? Binary means two. Bi for two. So we are looking at taking, at its simplest level, a metal and a nonmetal. Very, very simple. Okay, it doesn't mean the naming is necessarily simple, but a little bit easier with our binary ionics. Okay. What does ternary ionic mean? Okay, the ternary is implying three. Really what you should do when you think about ternary ionic is not two. Okay? And what's going to happen in a ternary ionic compound is that we are going to look, again, most typically at a metal, though there is one exception to that, and now a nonmetal group. Okay. So what do I mean by a nonmetal group? What do you neutralize an acid with? Base. What's your favorite base? Anybody know a name for a base? Baking soda doesn't work. That's not an IUPAC name. Okay, sodium bicarbonate actually works. So sodium bicarbonate, we have a sodium, there's our metal, and bicarbonate. What the heck is bicarbonate? Bicarbonate is our nonmetal group. We are grouping hydrogen with carbon with oxygen in a very particular pattern to generate what is known as a polyatomic ion. Okay? That polyatomic ion, you are going to be responsible for some of those. I doubt we're going to get to that list today, but you will see that in the slides later on. Okay? So you will have to know some of those for sure for this class. For other classes, I would recommend you memorize them all. And by all, it's 15, 20. Okay? And it's not just memorizing what atoms go into it. What else do you have to memorize? You also have to know the charges. And then also the name. Know that this is bicarbonate. Okay? So kind of be aware of that as kind of a looming structure in the future. Okay. So let's go through our simple stuff, because we should be able to do the simple stuff today. When we're going to look at the cations, now what we're going to do is name just the ions. So we're going to say monoatomic. Mono means one, atomic, we're looking at one atom. Okay? So we're typically looking at the metals when we look at the cations, because if we go back to our electron configurations, for a metal to look like a noble gas, typically the easiest thing for it to do is give away electrons and become positively charged. There's our cation. Okay? So most cases we're looking at our cations being metals. Okay? These are always going to be named by the parent or the parent element or parent atom followed by the word ion. So when we talk about sodium, okay, you'll notice that when I've talked about it, I try to talk about it with some extra words. I say sodium metal. Why am I saying sodium metal? Because I don't want you to think I'm referring to Na+. Okay, sodium metal is not charged. It's neutral. Right? Sodium ion is now Na+. So there's a couple big things that we'll note with that. First off, if we're going to refer to Na+, we'd start with sodium because the parent element of sodium plus is, or say Na plus is sodium. The next thing that we want to do is specify that we're looking at the ion, the positively charged species, not the metal. To do that, we add the word ion. Okay? So it should be relatively simple to go through and process these. How do you know it's charged? You'll look in the upper right-hand corner, and you will see a charge there. What if you see this? No charge, we're looking at sodium metal. If we put in the charge, now we're looking at sodium ion. So with our atomic notation, oops, this is going to be a problem. We had what, our atomic number in the upper left? Nope, it was the other way around, right? Atomic mass was our upper left. It was atomic mass and then atomic number. Anybody confirm that? Theory, you guys remember that better than I do. Okay, from our atomic notation. Did I do it right? Okay, mass is up in the top. So when we look around an individual symbol, we've got our atomic notation. Our atomic mass gave us what information? Protons plus neutrons. Lower left-hand corner gave us protons. Now we've got an extra piece of information. In the upper right-hand corner, this positive charge, when we combine it with the information of our atomic number, tells us what? The number of electrons. Okay? So within our notations, you'll see typically we leave off atomic mass and atomic number. We just run with the charges, okay, or no charges. The only time you'll see atomic mass and atomic number is if you move into the nuclear stuff. Okay? And I have no idea why none of you are not moving. We are actually over time, right? We're done at 40, right? Yeah. Okay. So apparently I was talking so much more interesting today.